Figure 8.1 shows a bar magnet suspended by a spring over a coil. The coil is connected to a sensitive center zero millivolt meter. The first part reads the lower end of the magnet is pushed down into the upper end of the coil and held at rest. During the movement, an EMF is induced in the coil. The meter shows a deflection to the right and then returns to zero. Explain why this EMF is induced. Easiest of them all, whenever you get a question like this, why the EMF is induced, all you can do is because there is a rate of change of magnetic flux linkage between the coil and the magnet. Alright, standard answer for any question like this. Because there is a relative motion between the coil and the magnet, that's why the EMF is induced. Or you can just answer it in terms of the cutting of the magnetic field lines. Alright, anyway, the answer would be acceptable. Then we have the next one, part 2. State what happens to the needle of the meter when, part 1, the magnet is released from rest and is pulled up by the spring. So magnet is released from rest and then pulled up by the spring. So there would be a negative rate of change of magnetic flux linkage. So whatever the magnetic field lines were there, now the magnetic field lines would be decreased as the magnet is being pulled up or away from the spring. What happens to the needle when the magnet is released from the rest and is pulled up by the spring? So in this situation, there would be a negative rate of change of magnetic flux linkage, so meter would deflect to the left side. And then we have the next one. The magnet continues to oscillate up and down, moving in and out of the coil with each oscillation. So the part B reads, figure 8.2 shows a transformer. The primary coil P connected to 240 volts main supply has 8000 turns. The secondary coil S supplies 6 volts to the lamp. So we can mark the data here. This thing is your VP, V sub P, primary voltage. This is N sub P, primary number of turns on the primary side, and this is your secondary voltage. And what you need to find is the secondary number of turns, the number of turns on the secondary coil. And you have the easiest formula from here, VP over VS equals NP over NS. Okay, then you insert the values and we'll hit it on the calculator. So 240 divided by, what do we have, 8000 equals 240 divided by 6 equals to 8000 divided by X. Then you cross multiply from there and you can find the value of X. For example, this 0 cancelled away with this one, and then you have 6 4s are 24, then 4 2s are 8, and would be 200. Anyway, you can just hit it as it is on the calculator and you can confirm the answer. Moving on to the next one. The current in the primary coil is 0.050 ampere. Calculate the power input to the transformer. So power input equals to the product of voltage and current. Since we are talking about the input power, so we'll be taking the input voltage or the voltage to the primary side. That was 240. So 240 times 0.050. So 240 times 0.5 would be half of it, 120, and then we take one decimal place back, should be 12 watts. 12 watts. Okay, then we have the next one. 90% of the power input to the transformer is transferred to the lamp. Calculate the current in the lamp. So what is the output power? We can first calculate the output power. We can find what the 90% of 12 is. This will give us the, what do you call that, output power. And 90% of 12 is, we need calculator for that. Okay, no, not 10.8 amperes, 10.8 watts. Okay, we're just finding how much 90% of the power is, so it would be watts. So this is the output power. So P out equals to 10.8, and from the formula we have output power equals to voltage on the secondary side times the current on the secondary side. What do we need to find from here? We need to find IS. Do we have the value of P out? Yes, 10.8. Do we have the value of secondary voltage? Yes, it was 6 times X, or IS, whatever you want to write it, and that would be 10.8 divided by 6. Then you hit it on the calculator and let me know what do we get.
1.8.
Okay, 1.8 amperes. Moving on to the next one. Another question from the transformer. Figure 9.1 represents a transformer. Part A says, name the process by which changing current in the primary coil P causes a changing current in the secondary coil S. That process is called electromagnetic induction. Okay, then we have the next one. Suggest a material used for the coils. So coil is basically a wire, a special kind of wire, because we wind the wire upon an iron core. So it is basically a wire. So what the question is, suggest a suitable material for the wire and explain why do we use that material. So the most suitable one for the wires, or for the what do you call that, coil, is copper. And the reason is because copper is a good conductor of electricity. The input to the primary coil P is 240. The turns, the voltage, and so I'm going to skip this one for you. This is just the same way. The resistor connected between the terminals A and B is replaced by 4 12-volt lamps connected in parallel. The current in each lamp is 1.5 amperes. Calculate the current in the coil P. Assume that the transformer is 100% efficient. Okay, so first of all, what we can do is we can find where the terminals A, B. Okay, so this is the output side, the secondary side. So this resistor has been replaced by 4 lamps, each with 12 volt, connected in parallel. So the voltage across each of it across all of them would be 12 volts, and the current flowing through each of it is 1.5 ampere. So the total current drawn by these 4 lamps would be 1.5 plus 1.5 plus 1.5 plus 1.5. So 4 times 1.5, which would be 6 amperes, 6.0 amperes secondary. So what we can say is the secondary current is 6 amperes. The secondary voltage is 12 volts, because in parallel circuit the voltage remains same but the current divides. So what do we need to find? We need to find the current in the primary coil. We need to find current in the primary coil. And the voltage in the primary side is 240 volts. So Vp equals to 240. Ip has to be found out. Vs is 12. Is 6 amperes. So first of all, let us write down the formula. Vp Ip equals Vs Is. So what was Vp? It was 240 times Ip, would be written as it is because we need to find it, and that equals Vs, which is 12, and the current was 6. Now we can do some of the cancellation, like 12 2s are 24, so you're left with 20 here. So Ip equals 6 divided by 20. Then you hit it on the calculator. We get 0 point something. 0.3. Sorry, this was to be written on the next part. So let me just copy paste it. Yes, with this one. So we get 0.3 amperes. Okay, then we have the next one. A solenoid is held in a vertical position. The solenoid is connected to a sensitive center zero ammeter. A vertical bar magnet is held stationary at the position X, just above the upper end of the solenoid, as shown in figure 10.1. The magnet is released and it falls through the solenoid. During the initial stage of the fall, the sensitive ammeter shows a small deflection to the left. Explain why the ammeter shows a deflection. Once again, the same question is being repeated. What do we write here? We can answer it in 2 different ways. Either we can say because there is a rate of change of magnetic flux linkage, or we can say because there is a cutting of the magnetic field lines of the coil of solenoid. So you can answer it either way. So I'm going to check this one. Then we have the next one. The magnet passes to the middle point of the solenoid and continues to fall. It reaches a position Y. Let me check the position Y. Okay. Describe and explain what is observed on the ammeter as the magnet falls from the middle point of the solenoid to the position Y. So if you remember, we studied a topic, a magnet falling through a solenoid, and over there we explained the way EMF is induced and the magnitude of the induced EMF and how does it vary with the motion of the free falling magnet. on the last part of this one, suggest two changes to the apparatus that would increase the initial deflection of the emitter. Easiest of them all, using a stronger magnet. For this situation, there is another one that is not compatible for all fit, but in this situation it is compatible if you increase the speed of the drop of the magnet. And in order to increase the speed of the magnet that is being dropped, you release the magnet from a higher point. Okay, so you just take the magnet to a higher point and then drop it from there. So the magnet would be having enough time to gain the speed, to gain more speed, and as it passes through the point X, it would be approaching the magnet faster. It would be approaching the solenoid faster, and hence there would be more induced EMF.